I think Chidambaram, I think you are because the session starts from 7 o'clock, so it's I start from 7 o'clock only. You can join early also, but so let us start today's session. That is live session number 7. So in the last session, we have seen the concept of maximum power point tracking and the impedance. How can we find the input impedance of various DC-DC converter that could be that from by which that we can implement the maximum power point tracking algorithm. So in today's session, we are going to see how we can control the impedance for maximum power point tracking. So as usual, we will first revise the big 7 content, and then we will solve the problems. So we know that input impedance is the function of output voltage and this duty ratio. So this sorry, one mistake is there. This is not R naught, this is V naught. So V naught and D are varying parameters. You can based on the load, these will vary. R naught value, so it is right. Sorry, R naught and D are varying parameters. So now the question comes is that how to generate appropriate duty ratio such that we can implement the MPPT. So they need to design controller block for performing this maximum power point tracking algorithm. And this is the typical block diagram for implementing the MPPT through DC-DC converter for a DC load. So here we have PV panel and we are sensing the current in voltage. Now with the help of this MPPT controller, we are generating the duty ratio from which that will decide the input impedance of DC-DC converter such that this load line crosses the maximum power point tracking, maximum power point of the IV curve. Now there are few typical methods that will be used for employing MPPT, and some of them are reference cell method, and in that we will see voltage scaling method and current scaling method, and other ones are voltage sampling method and power slope method and hill climbing method. Uh, can you tell? Can anyone tell any other MPPT method you know other than these methods mentioned here? Yes, one of the commonly used is the Butterman observe method, P and O method, and some of you might have heard about the incremental inductance method. So these four methods that we are going to see today, that are the most conventional one. So if you have understanding of these methods, then you can also understand the advanced methods that are uh, being used today or that you can see in the research papers. So coming to this reference cell method, so there are two types: voltage scaling type and current scaling type. And if you are tracking the maximum power point voltage, then you can call it as voltage scaling type. So then you call it as voltage scaling type. And if you are tracking this maximum power point current, then it is called as current scaling type. So first we will see the voltage scaling type, and then we will look into this current scaling type. So what is the concept here? If you see the IV characteristics and PV curve, then you can see that this open circuit voltage and maximum power point voltage, you can have some relations. Like you can assume that this maximum power point voltage can be very linearly with open circuit voltage by some constant. And here we have assumed it as 0.7. So, based on this assumption, our objective is that this VT should become VM, maximum power point voltage, to achieve the MPPT. So this is the assumption for voltage scaling type, and the objective is that you want this VT such that it become VMs, so that it will operate at maximum power point. So if you see the block diagram for this voltage scaling type MPPT controller, then you have one reference cell. So this one is reference cell. And from the reference cell, we are measuring the open circuit voltage, and it gets multiplied with some constant K to get this maximum power point voltage, and we compared it with this sensed signal, that is this output of PV module. Output of PV module, we compared with this output of PV module, and then we are having error, and error is being passed to PI controller. We will get some modulating signal, and then it is compared with carrier signal to get the PWM pulses. So before this comparator, where this carrier it is compared with the carrier signal, these are all the true signal. Means these are all before that, and after that there is transition. So here this is time conversion. So that means that you are giving this PWM pulses to DC-DC converter. So now if you see this comparator and this modulating signal, so here if you, what is the logic behind this to get the switching pulses? So if this modulating signal is greater than triangular pulses, and this triangular curve amplitude, then your switch should get turned on. And if this modulating signal is less than this triangular waveform amplitude, then your switch should be turned off. So in that way, we are getting the switching pulses for the DC-DC converter. So this is for voltage scaling type. Now we will see this current scaling type. So it is similar to voltage scaling type, but the difference that in the earlier case we are tracking the maximum power point voltage, but in this case we are tracking the maximum power point current. So that is the difference. So as we all know that this short circuit current is directly proportional to this photo current, and this open circuit voltage is proportional to logarithm of photo current. So this will be used later. Why this concept is discussed here. So here, if you see this IV curve, then so first one is the for a certain insulation. This blue IV curve is for certain insulation. Now you have decreased the solar insulation. Then you are getting the new MP point, new IV curve, and for that IV curve, this will be the new MPP point. So this will be the new installation. That's why it is told as ISCN and IMN, and this will be new MPP. So here you can see that this maximum power point current and this short circuit current varies, means you can assume it is varies with some constant linear, it is varying with some linearly constant K, and we can take it as 0.9. So here you can write Im upon Isc equal to Imn upon Iscn equal to some constant K equal to 0.9. Now, if you see the block diagram for this current scaling type MPPT controller, then again we are having with some reference cell. From there we are doing short circuit it, and from this short circuit of this PV cell we will get short circuit current and through a sensor, and it gets multiplied with some constant K, and that then we will get the maximum power point current, and that we will take it as reference signal. Now this reference signal is compared with the feedback signal. So this ERL will get generated. Now this it is passed through PI controller. So that then we will get this modulating signal, and it is being compared to carrier signal, and we will get the PWM pulses. So as like the previous case, what are the rule and objective? The rule is that this maximum power point current is varying linearly with this short circuit current, and we are assuming this some constant K, and we are taking it as 0.9. And what is the objective? Objective is that maximum power point current should match with this sensed current, sensed output current of PV module. So IT should become IM for implementing the MPPT algorithm. Now the question comes that which there are two types of reference cell method. Which one is better? So better is current scaling type, because Im equal to KISC we are assuming is much more accurate than Vm equal to KVOC. The reason behind this is that ISC varies linearly with insulation, whereas open circuit voltage varies logarithmically with insulation. So it is very important point. This current scaling type is better than voltage scaling type. This is because whatever the assumption we are taking, that we are relating with some constant K. So in the case of current, case of current type, it is more accurate than voltage type. It is because this short circuit current varies linearly with solar insulation, whereas this open circuit voltage varies logarithmically with solar insulation. Now coming to the sampling method. So this first method we have covered. Now the second method comes, that is sampling method. So in the reference cell method, what we are doing is that in reference cell method we are occupies very small area compared to solar array size. And suppose if something partial shading or some defects come in that reference cell, then it will give the some random value, and that will be not true for the solar module where we are implementing the MPPT. So during partial shading of due to nearby trees, the voltage given by reference cell will not accurately reflect the voltage of actual PV module. So this is the demerit of reference cell method, because we are taking one reference cell, and if this reference cell may not uh, be like to other PV module, it may having this shading effect or some defects. So it having whatever the sensed voltage, open circuit voltage and short circuit current is providing, that may not matches with the voltage or current of actual PV module. So to eliminate this demerit of reference cell method, we have to find some other alternative to obtain this open circuit voltage or short circuit current of the actual array. So the second method we are going to see today that sampling method, and in the sampling method we are also going to see this voltage sampling method and current sampling method. So let us see this first one, voltage sampling method. So in voltage sampling method, what we use one switch here in series with this PV module to this DC-DC converter, and we connect this one sense resistor such that we can measure the open circuit voltage for the module. Now, how we are going to implement the switching state for the switch? So what we are going to do? So let us so when this switch is connected to A, in that case we are measuring this open circuit voltage, and when this switch is connected to B, that is normal topology, and for which it is for which the DC converter is operating in MPPT. So for suppose here this is switching you can say this switching time for this switch given when for 1 microsecond it is connected to A pole, and for rest of time it is connected to B pole, that is it is in off state. So what is the duty cycle for this switch? So duty cycle will be 1 microsecond upon 1 second, it will be 10 to power minus 6. So it is, we can see that it is very a small value. Now during when this switch is connected to A pole, in that time we are passing to the sample and hold circuit such that it will provide this open circuit voltage. And this R sense is this value is very high. So you can say you can tell that this is approximately equal to the open circuit voltage of this PV module. Now let us see this current sampling method. In the current sampling method, we are doing the sample of current. So what we do here, they no need of this sense resistor. Just you have to short circuit the PV module. So you just when the switch is connected to A point, you are going to short circuit the PV module, and it is passed to sample and hold circuit. So it will give this short circuit current, and this average. Now how we will measure this current? So we have to take this average. So why we are taking this average? So this average will when this is connected to this A point, at that point there is no current passing through this DC-DC converter. You can say there is no current passing from PV module to this side. So this average, this block has the this will average out this impact of short circuit current for 1 microsecond duration. That's why we are doing the averaging. So we are getting the same value as this previous one. So due to this switch, we have to do this average block here. Is there any doubt? Anything you want to ask? Okay, what is, so there are so many, I have not gone through it. What is FC and FD? Can we call feedback as feed forward controller? So here, this FC and FD are the switching, are the frequency. this FC, the frequency of carrier signal, and FD is the frequency of the modulating signal. So this carrier signal should be much higher than this frequency of modulating signal. Otherwise, you will not get the better output or good. Means there is so much ripples at the output side. So more is the frequency of carrier signal, more you will get good waveform, and it is having less ripple at the output. Can we call feedback as feed forward controller? No, this feedback is not same as feed forward controller. It is something different. Please search book, journal, or link to learn referential and power slope method for learning and solving problem. Yes, FD is DC here. So in this case, this frequency of this modulating signal is 0 because it's DC quantity. But in suppose if you are having sinusoidal waveform, so in that case that will be useful. So I have shown here the general case. This carrier frequency should be greater than modulating frequency, much greater than modulating frequency, approximately 50 times, 100 times, 1000 times, like that. So for book or journal, Mohan, are you master student or PhD student? Okay, PhD student. So I have to see some good papers. I think might be sir has covered in his book. They have referred some references in his book. I think you can follow that references. But right now I have not referred to any research paper for this conventional type of MPPT algorithm. I'm not able to find impedance control MPPT. Okay, so I will try to see some of papers where they have uh, done analysis for this impedance control MPPT. Generally, these are basic conventional, means at the starting of PV technology, they have might done research. So nowadays, if you see papers, there will be very less. Nowadays, people are doing advanced things like they are implementing new MPPT algorithm that is based on perturbator method and incremental impedance method, and they are looking more into this grid connected PV system. For exam, I think whatever the assignment and the class lecture you are going through, you will able to get very good marks. I don't think there is need of reading extra apart from the course. If you are doing assignment, during assignment, you might face some doubts or some difficulties. But those who are keeping studying and solving the problems in the exam, it will be very easier for you. Right now, you may face some problems or difficulties while solving the assignment, but you are going through all the things honestly, then in exam, it will be very, how you can say, it is a cup of tea for you. So let us come to the third method, that is power slow method. So here what we are going to use, we are going to use the slope of power curve. The concept behind this power slope method is that we are using this slope of power curve, and if you see this slope of power curve at MPP point, it is 0. Like if you have some curve, suppose if you have some sinusoidal curve, so at maximum the slope will be 0, and before that the slope will be positive at any point, and after this maximum point slope will be negative. So we are going to use this concept for implementing the MPPT for this power slope method. So at MPPT, the slope of power curve is 0. So here this at MPP point, dp upon dvt equal to 0. And before maximum power point, that means to the left of MPP, we are having the slope positive, and that is dp upon dvt greater than 0. And after this MPP point, slope is negative. So dp upon dvt less than 0. So here now let us write the power equation. So power will be Vt into It, and let us take this derivative with respect to voltage. So you will get It plus Vt into dit upon dvt. So this is first equation. We are assuming it as first equation. And since we know that at maximum power point, this derivative will be 0. So putting this derivative equal to 0, you will get dit upon dvt, derivative of It with respect to Vt. At maximum power point, it will be minus it upon Vt. So this is the second equation. So from here you can say that slope of IV curve at MPP is minus it upon Vt. And one can verify also. If you see this slope, if you see the slope here, slope of IV curve at MPP, so it is negative. Mohan, I think your mic is turned on. So could you please turn it off? So this slope is negative. So it is minus it upon Vt, and its value is minus it upon Vt. So let us, this derivative of power with respect to voltage, we got this term. So let us assume this some constant rho. So if you want to implement this in digital domain, so you have to assume del dit upon dvt plus it upon vt, and in analog domain you can represent like this. Now we are assuming there is some DC-DC converter, that is that DC-DC converter is buck push. So the relation between input and output resistance is RT equal to R naught into 1 minus D upon D square. So therefore, we know that for buck boost converter, this whole IV curve can be means whatever the load line crossing through this whole IV curve, we can implement the MPPT for this whole IV curve. So at the duty ratio 0, this will be along the voltage axis, and when duty ratio is 1, this is along the y axis. So here you can see this, as this rho varies, duty ratio varies back and forth around MPP. And to narrow this gap, instead of normal op-amp, we have to use the hysteresis op-amp. So we will see this block diagram for power slope method, then you will understand this better. So before this point, we know this derivative of power with voltage is positive. That's why rho is positive here. And after this MPP point, this derivative of power with voltage is negative. That's why it is having transition at MPP point. If you see this rho curve, so here I am using the cursor. So before this MPP point, this rho curve is positive, and after this MPP point, this rho curve is, and this rho is going negative. So there is transition at the MPP point. Now let us see this block diagram for this power slope method, how we are going to implement this power slope method for MPPT. So here you are giving the slope of power with respect to voltage to this op-amp. So what you will get at the output? You will this output will provide this signal that varies from minus VCC to plus VCC, and this transition is coming at the MPP point. So now it is passed through this clipper circuit. So the clipper circuit just clip this negative part. So it is varying from 0 to VCC. Now what is the purpose of this gain block? So the gain block it will change the uh, the input from 0 to VCC to 0 to 1. So the input for gain block is 0 to VCC, while the output of this gain block we are getting as 0 to 1. So this gain value is 1 upon VCC. Now this is passed to this filter. The filter output will be this, and again this will pass through this comparator, such that this D2 ratio of DC-DC converter varies. So this is the block diagram for this power slope method. So here this we are using the hysteresis op-amp because this as this derivative is varying, this D2 ratio is varying back and forth around MPP. And if you want to narrow this gap instead of normal op-amp, you have to use this hysteresis op-amp. Now coming to the second method of power slope. So in the power slope one, there are so many derivative terms, and it is difficult to obtain derivative. Therefore, we go for method 2, where this power slope method is implemented without actually taking derivative of signal. So in the first method, we have used so many derivatives, but to obtain derivatives, it is very difficult. Therefore, we are going to see the second method, where we are not using any derivative term. So in the second method, we are using again some resistor. That value should be much higher than the output resistor. Why it is so? Because it should not draw that much current as compared to this output, as compared to the output load. So this resistance should be kept very much higher, so that it will draw negligible current as compared to this output load. And here one transistor is connected with resistance, and this transistor is acting as a switch. So here, if you see this first curve, this first load line 1 upon RT, that is cutting this IV curve at one point. So it is without considering this part, resistance R1 connected with this transistor. Now if you connect this resistance R1 in parallel with this capacitor CT, so this this is, let us take, assuming this is passing through this maximum power point. So this load line will be 1 upon RT upon R1. So this voltage ripple you will get like this one. If you are having this switch and we are giving the pulses like this, so this voltage ripple will be, you will get like this one. So now we are going to use this concept only. So let us implement for this power curve. So what? So again we are using this buck boost converter. So if you see this on the left hand side of MPP, this voltage ripple and power ripple are in phase. So we will get ripple in corresponding to the ripple in voltage. And the right hand side, this voltage ripple and power ripple are out of phase. So if you are using this transistor as a switch, then this voltage ripple, whatever you're getting at the right side and left side, you will not get the similar power ripple for the left and right side, because this, if you see this left side, the slope is positive. So if this voltage ripple is positive, at that time this power will be also positive for the left side. And this right hand side, the voltage ripple is positive, this power ripple is negative, because the slope is negative. So in other way, you can say that we are indirectly measuring the slope without using any derivative term. So let us see this block diagram for power slope method second. So here we are sensing this current and voltage output of this PV panel. So this voltage output will be something like this. There is some ripple in the voltage, and now we will pass through this DC block. So what is the purpose of DC block? This will block the DC part. So it will remove the DC part. So after removing the DC part, you will get waveform like this. So this average of this part is 0. Now you will pass it to zero crossing detector. So what is the purpose of this zero crossing detector? Since these edges of output from DC block might not be very sharp, so we will put additional zero crossing detector block to obtain the sharp edges. The purpose of zero crossing detector is that we want to obtain the sharp edge. So now this zero crossing detector output will vary like this for power and voltage. So for voltage and power, it will be different for left side and right side. Now if you combine both of them, since in the left side both power ripple and voltage ripple varies, will be in phase, so it will sum up. So if it will be sum up, like suppose here it is varying from minus VCC to plus VCC, so it will vary from minus 2 VCC to plus 2 VCC. And for the right side, it will cancel out each other, because voltage ripple and power ripple are out of phase for the right hand side of maximum power point. So both will cancel out and you will get 0 at the right side of this maximum power point. Now we will take this absolute value of this curve. So we will get the curve like this one. And now if you compare with this threshold value, so here we are using this comparator, and you will get waveform like this. And again, we are using the gain block to remove this VCC part that is coming from the op-amp. So this gain block having value is 1 upon VCC. So we will get the output as varying from 0 to 1. So it is pass through filter. So it is if it is pass through filter, this curve is obtained like this, and this duty ratio varies according to this curve. And this duty ratio varies such that this will be hovering around the maximum power point of this IV curve. Now coming to this last MPPT method, that is hill climbing method, that has been discussed in the lecture. So in this hill climbing method, we are using only this current and voltage values and calculate power for maximum power point tracking. So this PV curve is in the shape of a hill, and we will try to climb it either from right side or left side to reach the power point. So this name comes from the term hill, because this PV curve, it is similar to in the shape of a hill. So that's why it is named as hill climbing method, and we climb it either from right side or left side to reach this maximum power point. And here what we are doing it in this case is that, suppose we are initially set this power base as 1, power base to this 1 point. So here I mentioned, and if current is on the left side of maximum power point, then this duty ratio is decreasing. So if you go toward this maximum power point, then duty ratio is increasing, because here we can see that it starts from duty ratio 1 and it ends at duty ratio equal to 0. So as duty ratio decreases, this current power, peak current means this current power, and we want this current power, we want this current power to settle at MPP. We want this current power to settle at PM, or you can say maximum power point. So it is moving, this peak current is moving, and this P base we are assuming first, and then it will move according to this filter time constant. We will see the block diagram for this hill climb method also. So this P current point moves towards peak and touches P base on the right. So again, if touching the P base right, then again we start increasing D, because it touches the P base at the right side. So this P current again started again moving towards this left side, and again it will reach the P base to the left side. So it is keep moving along this line above this line of P base. So now with this process, we start moving this P base up to, say, you can say this P base 2. So initially it was at P base 1, and now upon moving along this curve, so we will move this P base 2 up, and let us assume this is P base 2. So again, we will vary D to reach MPP by narrowing down the region of oscillation by increasing this P base. So how you can implement this hill climbing method? So here you are sensing this current and voltage, and it gets multiplied. So here we are using two filters, slow filter and fast filter. Slow filter that means it is having high time constant, and fast filter it is having low time constant. So fast filter is measuring the current value of power, and slow filter that gives the output of P base. So both will vary automatically, but this P base is varying less and P current is varying much higher, because it is moving with this current mm, output of this PV curve, and it is passing through op-amp. Then when this P base is greater than P current, then there will be it will be saturated to VCC, and this P base is greater for P current for a lesser time. So that is for short duration, and again it will go down, because P current value is having higher as compared to P base. Now it is passed through this toggle flip flop, And let us assume this initial state as 0 and it is age triggered. So let us take it as age triggered. And initially it is 0. So sorry, it is 1. So upon getting this sharp and getting this edge, it will go down 0, and again after getting such a p base, it will again come back. Uh, Again you will get a similar type of this output for op amp. So it will again vary. It will go to 1. So this purpose of this toggle flip flop is that it toggles the duty cycle. And if you pass through this waveform, this to this filter, you will get the waveform like this. And again, you will compare using this comparator, you will get the PWM pulses to implement this MPPT algorithm. So till here, any doubt, anything you want to ask? How to choose P base initial value? So this P base initial value, I think this comes because here we are not setting P base directly. This is coming from this filter. This is coming from filter time constant. So based on the load, it decides. Based on the load and this filter time constant, this P base will come. So we are not directly setting the P base, but we are setting this this P base coming from this coming through this load, coming to the load connected to this PV module and this filter time constant. Is it clear, Mohan?
Yes, sir. Okay, sir, understood.
Okay. Okay, thank you. So any other thing you want to ask? Judge Mohan, Ramesh, Vikas, Deepak, Ruchi. So I have not covered today this housekeeping power supply in short notes, but due to less time, so you can go through these lectures. It is very easy, and get driver circuit also. Get driver circuit you will go. You can go through with transformer isolation and with opto isolation. Now we will solve problem for this session 7. So the first question comes say that which is more accurate scaling reference cell method, voltage scaling, current scaling method. You can type it on the chat box. Otherwise, you want to speak also, you can tell me. Yes, Mohan, correct, very good. So accurate scaling reference method is current scaling type. Why is it so? Because we know that this open circuit voltage is very logarithmically with the solar insolation, while this short circuit current varies linearly with this solar insolation. So this is more accurate. More accurate because ISC varies directly proportional to photocurrent, while this VOC varies logarithmically with this photocurrent. Mohan, you were from which college? Mohan, are you audible? Uh, Okay. I want conclusion from Mohan that you just PI controller to solve employee. You are employee. So in which problem you are getting the doubt in the current assignment or something else you have doubt? Okay. So I have to see the current assignment because it's duty of this course TA. We are here to only discuss the previous assignment and some we can go through doubts and discuss some theory and means quick revision for the session. So let us come to the second problem. So the second problem is that for the voltage scaling reference cell method, find the value of VT multiplied with 100 in volts within 2 decimal points for the specification below and the given controller in the diagram. So here you have shown the diagram and this specification is also given. We have to find this value VT multiplied with 100. So, and this voltage scaling referential method I use. So this is voltage scaling reference cell method. So here this is maximum power point. So this is not maximum power point, this is open circuit voltage. So open circuit voltage is multiplied with voltage scaling factor K1. You will get this maximum power point voltage and you have to compare with the sensed voltage and it is plus proportional gain. So let us solve this problem. So according to this controller block diagram, you can write D value. So D value is coming as K1 into V1 minus Vt and it is multiplied with K. So this one is first equation. And we know this and the converter is buck boost converter. So small d here, you can take it as this time signal. So we have to play with this actual signal that is DC ratio coming before this before this carrier signal being compared. So D2 ratio it is coming like this. Now We know that this for buck boost converter. Now for this buck boost converter, output voltage is input voltage multiplied with d upon 1 minus d. So this is the second equation. Now with these two equation, you can find the Vt. So what we can do is that we can write this second equation in term. We can write this in terms of d. So d will come out from here as V naught upon V naught plus Vt. So this is second equation. So from first and second, you will get V naught upon V naught plus Vt equal to K1 V1 Vm minus Vt into K. So put all the values. So V naught is 15 and V naught is 15 plus Vt equal to K1 is 0.7, Vm is 32 minus Vt is we have to calculate in K is 10. So if you do simplification, you will get you get quadratic equation. So 10 Vt square minus 74 Vt minus 3345 equal to 0. So from here you will get two voltage, two terminal voltage. One is Vt equal to 22.35 35985 volt. Another one you will get minus 14.95 95985 95985 volt. So this will be considered, this is not being considered. So here in this question it is asked that Vt into 100. So the final answer will be 2235.985 volt. So this is the answer for this problem 2. Now coming to this problem 3. From the specification of question 2, find the error K1 minus K1 V1 minus V2 into 100 with the proportional controller. Okay, general PI controller. So I will try my best to cover in the next session. PI how we use this PI controller generally in industry and in many applications. Why it is so much widely used and what is the significance of pole and zero in the PI controller. So why it is most, you can say it is universal type controller. So I will cover this part with the transfer function and all these things. So now this one is very easy. You know this VM VT K1, you have to find this error at this term. So this is very easy question. So we have VM value as 32 volt, K1 as 0.7, this VT as 22.3598. So you have to just put the values and get the answer. K1 is 0.7, VM is 32 minus VT 22.3598 into 100. So it will be 4.02, the final answer. Now let us come to the next problem. From the specification of question 2, find the duty cycle D within 3 decimal points. So duty cycle for buck boost converter is V naught upon V naught plus VT. V naught is given as 15. 15 plus Vt is 22.35. 3598. So you will get answer as 0.4015. Now let us see the next problem. So this is good problem. Which of the following circuits will provide the output voltage waveform with respect to applied gate driver voltage waveform as shown in the figure below? So this is the gate driver voltage waveform where this VG denotes here and output voltage coming like this. So you have to tell which of the following circuit will replicate the similar behavior. And let us assume this as it is option A, and this is option B, and this is option C. So how we analyze the circuit? So let us first, for this gate driver, let us first it is having high value. So when it is high, and this is NPN transistor. So when it goes higher, it will turn on, and this is grounded. So output will be low. But here you can see in the waveform, when this gate driver uh, output is high, this out V2 is also high. But here we are getting opposite behavior. If it is high, then we are getting low signal. So this will be not correct option. Now coming to the second option, let us take, we are providing the high signal from the gate driver. So it is NPN transistor. So NPN transistor, it will get turned on, and here it will coming, this point will come as ground, and this is PNP transistor. This is PNP transistor. So this is ground. So again it will turn down because this is PNP transistor. It will turn down. So this, if it get turned down, so this point will come as VDD. So this will be VDD. So here this VDD come. So now based on the transistor type, so it is PNP and this is NPN. So here if it is VDD and this is VDD, so if this is VDD, so here you can see this ground, so it gets turned on. So if it gets turned on, lower transistor get turned on, then output will be low. So the input is high, output is low. So again, it does not matches with the given gate driver voltage waveform. So now coming to the C option, so this is also incorrect. In the C option, from the gate driver, you are providing the high input. So here this transistor type is NPN. So if you provide high input, so it gets turned on. So if it gets turned on, this part will be ground. So this is a ground. So, and this is PNP. So this is PNP type. So it gets turned on. So this will be VDD. So this, sorry, this, it gets turned on. So this will comes as V naught comes as VDD. So V out is high. So V out is high. So both input and output are high, and it matches with the given output voltage waveform with the gate driver voltage waveform. So this first one by the gate driver voltage waveform. This was the input signal, and this lower one is the output voltage waveform. So both are high or both are low. So that is matching with this C option. So C option is correct. Now coming to the next problem. I hope you all try this problem. This is very easy. And if you have gone through this power slope method, then you are easily able to solve this problem. So here for the IV characteristics of PV panel, find the terminal voltage in volts at which maximum power point happens. So here this IV characteristic of PV panel is given. You have to find the terminal voltage at which maximum power point happens. You have to use the characteristics of PV curve. If anyone got the answer, please tell me. So let us try with this first method at maximum power point. At a maximum power point, we know that dV upon dV equal to 0. So this will be, let us first find VI power. So it will be minus 0.1 VQ plus 24.3 V. So this dP upon dV will be minus 0.3 V square plus 24.3. So if you get to 0, then you will get V equal to 24.3 upon 0.3. So we will get V equal to under root 81, that is 9 volt. And some of you may apply this one. Direct this relation at MPP. We know that di upon dV equal to minus I upon V. So di upon dV, what it will be? It will be minus 0.2 V and 24.3 will be 0. So it is minus 0.2 V and minus I. So it will be 0.1 V square minus 24.3 upon V. So it will be minus 0.2 V square equal to 0.1 V square minus 24.3. So it will be 24.3 equal to 0.3 V square. So you can apply both method. You can directly write this power slope at MPP point is 0, and you can also write this di upon dV equal to minus I upon V. So you will get V equal to 9 volt. Both methods are correct, and from both methods you are getting the same answer, right? Please all of you try. These are very easy problems. Don't means like present virtually. You should be somehow little bit active. So let us come to the next problem. For question 6, find the maximum power point. So we have found the MPP voltage. So power is VI, and VI we got. So we can 0.1 V square plus 24.3. So 0.1 VQ plus 24.3. So V equal to 9 volt. V equal to 9 volts. So it will be minus 0.1 into 9Q plus 24.3 into 9. So we will get minus 72.9 plus 218.7. So we will get 145.8 watt. Now for this problem, for the question 7, for V equal to 7 volt, select one of the following options. Options are dP upon dV greater than 0, dP upon dV less than 0, and dP upon dV equal to 0, none of the above. So I want this answer from your side. So please try to answer chat box. I think only Mohan is active. Mohan, can you type the answer in chat box? Is the question clear to you what I am asking? So the maximum power point voltage for this problem is given as 9 volt. So VM they have provided 9 volt. So they are asking for voltage of 7 volt. Which of the following option is correct? I don't think there is so much time it will take. No, you can directly calculate. If you know this VM, if we are knowing this VM value, if we are knowing this VM value, that is 9 volt, and do you know this VM value is, at this VM value, slope is 0. And before this VM value, the slope will be positive. And after this VM value, slope will be negative. So you can directly say that A option is correct. Other way you can find is that you can go through the relation. Power we know that 0.1 VQ plus 24.3 V. So dP upon dV equal to 0.3 V square plus 24.3. So dP upon dPV upon, at the V equal to 7. So it will be 0.3 7 square plus 24.3. So it will be minus 14.7 plus 24.3. So you will get 9.6. So it is having value greater than 0. So A option is correct. Any doubt? Yes, A is correct. Thank you, Mo. So let us see the next problem. Now for the question 6, for V equal to 14 volts, select one of the following options. And the options are dP upon dV greater than 0, dP upon dV less than 0, and dP upon dV is equal to 0. And D is none of the above. So which one you think it should be correct? Yes, Mohan, because you are correct. B is correct. You can also find it is beyond the MPP point. You can also find numerically. So V equal to 14. So it will be minus 0.3 V square plus 24.3. So it will be minus 0.3 into 14 square plus 24.3. So it will be minus 58.8 plus 24.3. So it is having less than 0. So it is negative. Its value is negative. Now come to the next problem. From question 6, for the power slope method to control as shown in the lecture, select the values for which the output of comparator after absolute value calculation is positive. So you have to recapitulate this power slope method too. Means if you see this power slope method too, so here we are talking about means this at right hand side, this slope is positive. So it means that we are talking about this right hand side. So as we know that the slope after this maximum power point voltage slope is positive, and before this maximum power point, before the maximum power point, slope is negative. And we are given with maximum power voltage as 9 volt. So we have to see the left, we have to see the right side. So it is Vm is given as 9 volt and slope is positive at right side. So only one option is coming greater than 9 volt, it is 12 volt. So B option is correct, and all the values are less than 9 volt. So A, C, D are incorrect options. Now let us see the next problem. A PV panel of 250 watt has an open circuit voltage of 37.5 volt and short circuit current of 9.6 ampere. If the slope of IV characteristic at maximum power point is minus 0.269, then current drawn from the panel at this operating point is approximate to 2 decimal places. So what are the things here given? So this maximum power is given as 250 watt and open circuit is voltage given as 37.5 volt. Short circuit current is given as 9.6 ampere. If the slope of IV characteristics at maximum power point, so this one is also given di upon dv at the rate maximum power is given as minus 0.69, minus 0.269. Then current drawn from the PV panel at this operating point is. So we know that at MPP di upon dv equal to minus I upon v. So you can also write it as minus Im upon Vm. So this will be one relation minus 0.269. So this you can tell one, you get first relation, and Pm equal to Vm into Im, and Pm is given as 250 watt. So Vm into Im. So this you got second relation. Now we have to just use these two equations from equation first and second. So 250 equal to Vm. So we want to know the current. So let us write in the current form only. So 250. So Vm will be 0.26. Vm will be Im upon 0.269 and gets multiplied by Im. So it will be Im square upon 0.269. So therefore Im will be 0.269 into 250. So it will be 67.25. So it will be 8.2 ampere. 8.2 ampere is the answer. Now let us see the next problem. I think related with the previous problem. So here referring to question 11, terminal voltage of PV panel at MPP. So once you know this maximum power point current, it is very easy. Maximum power point voltage you have to find. So PM we are given with 250. You have to find Vm, and maximum power point current is 8.2 ampere. So Vm will be 30.48 volt. This is the answer. Now let us see the next problem. So again it is related with the previous problem. So here referring to question 11, the PV panel is operating at 184 watt. So this power is different than maximum power point volt, maximum power. Maximum power is 250 watt. And this operating power is 184 watt. And at a point with gradient of power between terminal voltage is 8.2 watt per volt. So dP upon dV is given as 8.2 watt per volt. And gradient of voltage with respect to current is given as minus 20 upon V upon A. So you can write di upon dV equal to minus 0.05 ampere upon V. So these things you are given. You have to find the terminal voltage of panel at this operating point. So you have to find the voltage at this point. So you have to use the relation of power slope. So let us just revise. So we know that dP upon dV equal to I plus V di upon dV. This comes from power equal to VI equation. And this power is given as 184 watt. So here dP upon dV is given. So it is 8.2. I we have to find V, we have to find, and slope of di upon dV is given as minus 0.05. 8.2 equal to I minus 0.05. So this is the one relation and this is the one relation. So from first and second, you will get I equal to 184 point V minus 0.5 V. So it will be 8.2 V equal to 184 minus 0.5 V square. So 0.5 V square minus 8.2 V minus 184 equal to 0. So you will get two voltage. One is 20 volt and one is minus 184 volt. So this is considered, this is not considered. So the final answer will be 20 volt. And the maximum power point voltage is 30.48 volts. So it is less than this maximum power point voltage. Clear any thing you want to ask? So let us see the next problem. So the next problem is that referring to question 3, the current transform the people. So it is related with the previous problem only. So referring to question 11, question 13 you can write. Referring to question 13, current drawn from the PV panel because it is not operating at maximum power point. So it is very simple. I equal to P upon V. Power is given 184 watt. Voltage we got 20 volt. So it will be 9.2 ampere is the answer. Now let us see the next problem. So here a reference cell current scaling method is used for MPPT controller to extract maximum power output of a PV panel. It is found that the short circuit current of the panel is 1 ampere. So let us first write what are the things given. So short circuit current is given as 1 ampere at 1 kilowatt per meter square. At insolation of 27 degree at 27 degrees Celsius. What is the approximate value of current IMP at maximum power point at insulation of 1.5 kilowatt per meter square at the same temperature? Consider the current scaling factor IMP upon ISC is 0.6. So the K value is given here. So here we will use one basic relation that if you see the ideal characteristics of a PV cell, then this is photocurrent. So if you short circuit, then the short circuit current this short circuit current is directly proportional to this short circuit will be equal to photocurrent and this photocurrent directly proportional to insulation. So that means this short circuit current is directly proportional to insulation. So here this short circuit current at solar insulation of 1 kilowatt per meter square is given as 1 ampere. So ISC equal to 1 ampere at the solar insulation of 1 kilowatt per meter square. What is the short circuit current value? at solar insolation of 1.5 kilowatt per meter square, it will be 1.5 ampere. Here we have to find the IMP. So IMP will be K into ISC. So K value is given as 0.6. ISC we got 1.5. So it will be 0.9 ampere. Therefore, C is the correct answer. How many of you got this answer? Let me know. How temperature given is same in case if temperatures are different. How to calculate? Okay. If temperatures are different, then we have to use this relation that we studied in the big 2 or big 1. But temperature coefficient in that case it is given. We have studied this relation, this current coefficient alpha is change in ISC upon ISC at 25 degrees Celsius upon delta T into 100. So if there is change in temperature, then we have to use this relation. First, you just find the short circuit current with respect to some insulation here given 1.5 kilowatt meter square. And after knowing this short circuit current at this solar insulation, you can find this. You can use this. You can use this expression having this temperature coefficient. But temperature coefficient for current it should be given in the problem. And from there you can find the short circuit current at at different temperature. So it may be different, like in this problem it is given 27 degrees Celsius. So you may consider it as T degrees Celsius. Or 27 you can say, the whatever it is given in problem. Okay, Mohan. So let us see the next problem. At maximum power point, the slope of power versus voltage curve of a PV cell is. Again, it is very easy. Please tell the answer. Yes, Vikas, Mohan, you're correct. Correct answer is 0. Now again, this one is also easy problem. A PV panel is connected to a buck boost converter and the output of buck boost converter is connected to an inverter to supply a motor load. It found that efficiency of buck boost converter is 90% and efficiency of inverter 80%. What is the overall efficiency of total system? So efficiency of buck boost is given as 90% and efficiency of inverter is given as 0.8, 80%. So what will be the overall efficiency? Total efficiency so 0.8 into 0.9, it will be 0.72 or 72%. So D is the correct option. Now we are left with 3 more questions. Just I think all of them are easier one. Yes, Mohan, you are correct. Very good. So let us see the next problem, question 18. So the power versus voltage curve of PV panel is approximated to an isosceles triangle with the peak. So here, sorry. So here we are considering this power versus voltage curve and isosceles triangle with peak power occurring at 0.5 VOC. It is VOC. And if the panel has peak power of 40 watt and open circuit voltage of 40 volt. Therefore, maximum power is occurring at 20 volt. What is the value of dP upon dV to the left of maximum power? So here you have to find the dP upon dV to the left of maximum power curve. So dP upon dV will be, you have to just find the slope. Slope will be, here there are 2 points. So one point is 0, 0, other point is 20, 40. So 0, 0 and 20, 40. So it is x1, y1 and it is x2, y2. And we know that slope is y2 minus y1 upon x2 minus x1. Y2 is 40, y1 is 0, x2 is 20, 0. So it will be 2 watt per volt. So the correct answer is 2. Let us see the second last problem. The power versus voltage curve of I think it is repeated or what? Oh, I think there is a mistake here. So I will solve this 1920 problems. I think there is some mistake in typing the question. So I will solve this problem and then I will upload the session. It is very easy 1920 problems also. So I just want to close today's session here. And anything you want to ask, please ask. Mohan, you are asking about which problem. If I can help you, then I may suggest something for current assignment. So you can also contact me on WhatsApp. It's very convenient. So it is my WhatsApp number. So you can contact me there also. You can either way you can contact either email or WhatsApp, both way, whatever you that feel convenient. Any other thing you want to ask? I have not covered today good problems. I think that because I don't know all problems are I think very easier one. But some problems are really good from this MPPT algorithm. So if you know the basics, I think you are able to cover the good problems also. Okay, all right. So okay, good night, and we will meet in the next session at the same time. Thank you for attending the session.